Okay, so the third paper is titled Quantization Guided Training for Compact tinyML Models. It will be presented by Sedigh GHAMARI. So Sedigh is an AI research scientist at Latent AI. He received his PhD in theoretical physics from McMaster University in Canada. During his PhD, he was affiliated with the Canadian Institute for Advanced Research, CIFAR, and the Perimeter Institute, PI. So Sedigh, please carry on.
Thank you, Jason, for the kind introduction. It is my pleasure to present the work I've done together with my colleagues at Latent AI on extreme compression of deep neural networks for edge inference. A little bit about us. We are a startup that specializes in adaptive AI. So let's just start with the main challenges with inference on the edge. As we all know, deep neural networks have become the de facto solution for a lot of applications. However, they come with the downside of being very resource intensive. At the same time, when it comes to the edge devices, we often, almost invariably, faced with limited compute and memory resources. To make matters worse, often these edge devices are battery powered, and we have to be cognizant of the power draw. And this is something that you probably have heard already many times in the previous talks, which emphasizes the importance of these factors. So not surprisingly, various approaches have been considered to alleviate these issues. Perhaps most notably is the idea of quantizing model weights. So very briefly, what we mean by quantization is that representing the model weights, instead of using float 32, we would represent them using fixed point, often 8-bit integer or even lower bit representations. So if you kind of survey various frameworks that are available out there, what you find is that, at least up until now, post-train quantization has been the dominant approach. And what we mean by that is you train your model in float 32 as if you're going to deploy it at float 32. And at the end, you quantize your weights in a rather ad hoc manner to your desired or target number bits. Usually it works perfectly well at 8 bits, and in some cases when you're doing, and of course, like above that, for example, if you quantize to floating point 16. However, the model performance degrades very rapidly once you go below 8 bits. So, and the reason that you might be interested in that is when you want to kind of opt for an extreme compression of your model. So to alleviate this shortcoming, something that a host of approaches that are that go under the broad title of quantization-aware training approaches have been proposed. And basically, what we are presenting here is another quantization-aware training. But before kind of delving into what approach we are presenting, I wanted to kind of take a step back and tell you a little bit about, or at least offer you a visual guide as to what we really are doing when we are quantizing a model parameter. So what you're seeing here on the right-hand side, the sort of the blue histogram. So this is the histogram of the model weights. So this could be, you know, let's say, a convolutional kernel with tens of thousands of parameters. As you can see, the blue one is in FP32, and when you quantize it, for example, in this case, we quantize it using an asymmetric quantizer at 4-bit, and what you end up with is effectively 16 bins. So this is basically the extreme compression that we are aiming for, and even less than that. All right, so let me tell you a little bit about the motivation of the approach we have developed. So we started on this path with a few key objectives in mind. Specifically, we wanted to maintain performance, which is common to any other quantization-aware training. But we also wanted to provide support for various quantizers. As we all know, it's not like it's not that one size fits all. So different target devices may lend themselves better to various quantization approaches. Of course, asymmetric and symmetric quantizations are the popular ones out there, but that doesn't necessarily mean these are the only ones. So certain target hardwares might benefit from other quantizations. So we definitely wanted to have support for any form of quantization that you might have. A good example of that would be, for example, powers of 2, where you represent your bits with pure powers of 2. In that case, multiplication reduces to bit shifts. The other the other objective we had in mind was the discovery of mixed precision layouts. So what I mean by that is you don't have to quantize all your model weights at, say, 8 bits or 4 bits or 2 bits. It could be that you may have an information bottleneck of sorts. So you have to keep one of these weights at a higher bit representation to better maintain your accuracy. And the flip side of that is going to be that some of the weights may not be as essential, so you can aim for a more aggressive quantization. So we wanted an approach that allows for ideally almost automatic discovery of these sort of opportunities for extra compression. And lastly, and kind of more towards a pragmatic side of things, a practical side of things, we wanted an approach that's not tied to a specific framework. We want it to be flexible enough that can be implemented easily and ported easily in various frameworks. So you're not limited to, say, TensorFlow or PyTorch or MXNet or what have you. So the approach we came up with is a regularizer-based QAT that we adopt Quantization Guided Training, or for short QGT. What it does is that it attaches what we call a quantization loss node to your model weight. This is, I should emphasize at this point that this is somewhat distinct from some of other regularizer-based approaches in that we are relying on what we call dequantized weight. And by dequantized weight, what we mean is that you quantize your floating point 32, and then you map it back onto the floating point 32. So that would be this WQ. So both W, the original weights, as well as WQ, the dequantized ones, are in a sense in the same space. And that becomes hopefully more clear in the next few slides. So basically, we attach these quantization loss nodes to model weights and bring them into the task, add them to the task loss together with these sort of weighting parameters, lambda i's. I should note at this point that even though in the framework allows for various lambda i's, in practice, one of the things we have discovered is that you could use the same hyperparameter for the whole model. So it doesn't have to be that you have a single one, but you have that flexibility at the same time. So how does this compare against perhaps the most popular version of QAT approaches out there, the so-called straight-through estimator-based QAT approaches? So on the right-hand side, I have basically a rough depiction of what a straight-through-based estimator QAT approach does against what we have. So as you can see, these STE-based QAT approaches require inserting these straight-through estimator quantizers into the model graph. So what happens is that you keep your weights at FP32. In the forward pass, this STE quantizer quantizes it. However, when it comes to the backward pass, you just accumulate them, so it's as if it doesn't exist. So that's why it's called a straight-through estimator. And you basically gradually accumulate sort of weight updates, and that's how you're able to sort of nudge the model towards something that to basically recover your performance. However, our approach, as I mentioned in the previous slide, is based on attaching this regularizer without really invasively inserting it into the model graph. So that's a point that I think is worth mentioning here. As you can see on the figure on the left-hand side, you are rather invasively inserting these nodes, and this ends up being, in practice, a hurdle in how you implement these approaches. Because if you think about the workflow, what you're doing is that you're bringing in your model, you have to insert these, which may not be, well, oftentimes it's not easy. In fact, almost is not easy to do. And at the end, you have to remove them to restore your computational graph. However, what we do is that we just attach them without actually meddling with the graphs. So, which makes attaching them and removing them much more easier. And lastly, one of the benefits of this approach is that since we are using quantization loss, we are able to discover the opportunities for mixed precision that I mentioned earlier almost automatically. So if you, in the course of training, look at your quantization loss terms for various weights, you can see that some of them, for lack of better words, tend to be more stubborn. And that basically tells you those are the ones that are less amenable to quantization. So basically, if you want to opt for mixed precision, you could start with the lowest bit precision that you're willing to go for, say 2-bit or even a single bit, and then identify the ones that are less amenable to quantization at that number of bits, and then kind of represent them with higher number of bits. Right, so now let me switch gears a little bit and kind of try to give you some intuition about how QGT and STE-based QAT approaches stack up from a more mathematical perspective. So what I'm showing you here is a depiction of model weights. So of course, I'm using 3 axes here, but in reality, you have tens of thousands of axes. So this subspace is what we call quantization invariant subspace. So that is the points, the configurations of your model weights that once your system is on, if you quantize it, nothing happens. So what we mean by that is, so think of it as a case that your weights are already perfectly binned. Now this blue point here, this indicates your optimal point, the task optimal point without any constraints. So this would be basically when you train your model at FP32. What you're doing in post-training quantization is that you immediately project this onto this quantization invariant subspace. And obviously, there's no guarantee that this is the most task optimal point on this manifold. And that's why oftentimes when you do PTQ under 8 bits, your task performance drops dramatically. Now, what do STE-based QAT approaches are doing? So what your model sees, just because your model weights are behind the STE quantizer, is basically being constrained to this submanifold. So basically, your training trajectory is constrained to the manifold. So, and it's imaginable that in some cases, this ends up being too stringent on training and impedes your training. Now, how does QGT compare against those two? QGT is not really constrained. So in a way, you can think of it as, relaxing that extreme projection, at least as far as your forward pass is concerned. Therefore, your model will have extra trajectories or more paths available to it to converge to that point. So from a purely mathematical perspective, I think one can argue that there are benefits in kind of not really constraining your model to this subspace of quantization invariant weight configurations. Right. Now let me go back to the parameters that I mentioned earlier that this QGT approach involves. So these lambda i's. So you might wonder, okay, so this simplifies the task of developing extremely compact models, but how does this obviously, if you have too many hyperparameters to tune, then this is going to be a problem. So that was one of the aspects that we worked on a lot to find an answer of. And this is what I'm trying to show you. So, and this kind of ties into what I showed you earlier. So if you set lambda to 0 in this approach, what you're getting back is your post-training quantization, because really what you're doing is that you're just training your model without any constraints. On the other hand, when you take lambda to infinity, what you end up with is something that's more of a projection-based QAT approach, which you can also think of it as being the same as the forward pass of QAT. So except for the backward pass of STE-based QATs, if you take lambda to infinity, you get the same thing. So this figure here kind of tries to depict that. If lambda is 0, so here's the lambda, the vertical axis is your performance, and the horizontal axis is roughly, you can think of it as training time in a loose sense. So obviously PTQ doesn't do anything. If you take lambda, choose a very large lambda, what will happen is that early on, and I'm assuming that you're starting from a pre-trained model. That's why your performance is already high. So if you start with a very large lambda, your performance drops dramatically, just because the large lambda will effectively project your model onto that subspace or very close to it, and then it will take it some time to recover. However, turns out in between there is this optimal lambda that would kind of gives you an optimal training time, even though it's not very easy to quantify that due to the presence of many other parameters. And of course, lots of variability from model to model. So empirically, what we have found is that if you choose your lambdas, or it could be a single lambda, such that this term is comparable to this term, and oftentimes not more than 5 times larger, you don't have to worry about precise tuning of these, and you get almost an optimal training trajectory. Right, so let me share with you some of the preliminary results that we have. Remember, our first objective was to have a QAT approach that basically preserves performance. So we kind of looked at a number of tasks. We looked at ImageNet and the 10 class smaller case ImageNet. We looked at grayscale and as well as RGB, and we also examined some of the most popular computer vision architectures out there. Basically ResNet 50, MobileNet V1, and later on I will show you results on MobileNet V2. What I'm sharing with you here are the FP32 results, as well as the top 1 performance at various quantizations. So here for MobileNet V1, this is at 4-bit. Per tensor quantization, we get about 8 times reduction in size, and we only lose about 2.2% in accuracy. Similarly, we have very reasonable results, very good results for other quantizations. For example, for the 10 class, this is MobileNet V1 with the width multiplier of 0.5. Same thing with the one below. And we have close to 7.3, and the reason it's not exactly 8 just because it's per channel, so you tend to have a little bit more in terms of number of parameters. The other thing I want to draw your attention to is that, with the exception of ResNet, which starts with about 100 megabyte in terms of model weight, all the results that we're getting is basically sub-megabyte. Let me also kind of draw your attention to what happens to the histogram of model weights. And this is very, in my opinion, interesting. So what we have seen is that if you compare the FP32 fully trained histograms against the ones that are trained under QGT, what you see is that in some of them, it's effective. It at least appears, even though this is not exactly, this may not be, this is one way of looking at the parameters. It appears that what you're getting is similar to post-training quantization. However, in some cases, like the bottom right histogram here, you can see that the the train model, the histogram of the train model has to kind of stretch itself outwards to kind of maintain the performance, which is interesting. This tells you that most likely with no level of fine tuning, at the end of PTQ, you can recover model performance. And finally, let me share with you a case study that we worked on based on this QGT approach. So we wanted to develop a tiny person recognition system. So think of this as a visual wake-up word. And obviously, the input size has to be very small. So the input size in our case was 96 by 96. The data set that we used was derived from MS COCO 2014. And the architectures that we examined were MobileNet v1 and MobileNet v2 with a width multiplier of 0.25. And our goal was to go below 100 kilobytes while maintaining reasonable accuracy. I also should point out the reason that we want to keep the accuracy as high as possible is that usually these systems are used to sort of invoke another system. So if there are too many false positives, you end up basically draining the battery. One of the things we noticed was that because we are going for such a small images, we had to kind of be more judicious in picking the threshold for the size of the largest instance of the object. So that's what this histogram indicates. So we set the threshold to about 20% of the image size, and that translates to about 100 pixel from top to the bottom. So basically, that was the pre-processing that we performed. And what I'm showing you here is the comparison between 4-bit. Everything here is in per channel, post-train quantization, and also we have 2-bit quantization results here. PTQ against QGT. So what you can see, for example, MobileNet v2, we lose about 3%. Reduce the model size by about 18 times, and by quantizing it to 2 bits. So with that, I thank you for your attention. I'd be happy to answer any questions you may have.
Thank you, Sedigh, for a very good talk. The floor is open for very quick questions as we are tightening the timing right now. So I have one quick question. So is your basically this technique, is it available in GitHub? You know, if you want to use or anyone?
Right. So this is part of actually our SDK. It is not open sourced. We are in the process of offering the models that I showed, open sourcing them on our GitHub, Latent AI. But if there's any interest in this approach, please reach out to me. We'll be happy to provide the SDK for kind of like evaluation.
Perfect.
Again, just a quick shout out to our sponsors. Bear with me for 1 minute. We have different categories. We have executive sponsors. First one being ARM. Then we have Qualcomm. We have Samsung. Platinum sponsors. Ada Compute. Lattice Semiconductor. Gold sponsors. BrainChip. Babel Labs. DSP Group. Edge Impulse. EMSA. Gray Matter Labs. Greenwaves. Hymax. Imagimob. Latent AI. Maxim integrated, Quixo, Reality AI, SensiML, Silicon Labs, Sentient, Google TensorFlow, XMOS, and lastly, silver sponsors, Edge Cortex, Hotchi, and SynSense.